Hey everyone, here we are with our next video. This one is the last one for the identities section that we have going on here. So this one will be 6.3 and it covers three different kinds of identities that we'll look at, or formulas. I know your book calls them formulas, but a lot of other books will call them identities. So in this one, we're going to talk about the double angle, power reducing, the half angle, identities, or formulas. Your book goes in the order of first they do double angle and then power reducing and then they do half angle. So the homework kind of goes in that order as well. Just out of my personal preference, I'm going to do the half angle ones first. So first I'll just introduce these to you. So these are the half angle formulas or identities. Sine alpha divided by 2 is equal to plus or minus the square root 1 minus cosine alpha over 2. Cosine alpha over 2 is equal to plus or minus the square root 1 plus cosine alpha over 2. And then we have tangent alpha over 2 is equal to plus or minus the square root 1 minus cosine alpha over 1 plus cosine alpha. We have another option for the tangent half angle identity. We also have 1 minus cosine alpha divided by sine alpha. And we have sine alpha divided by 1 plus cosine alpha. The reason that I'm going to start with the half angle identities is because we did some things in the last section, 6.2, with the sum and difference. We used identities to find the exact value of angles that didn't have a reference of 30, 45, and 60. So what we're going to do here is we're going to do a very similar topic to that. We're going to do exact values of weird angles that don't have references of 30, 45, or 60, but we're going to use the half angle identities instead of the sum and difference. The other identities that we're going to look at, the double angle and the power reducing, those aren't really used for that kind of problem. So that's why I want to start with the half angles, because those are used for the same kind of things that we did in the last section. So just a reminder as well that I do have these on the identity sheet, so you do not have to memorize these. So this will be example 1 in our section. We're going to find the exact value, and the first one that I'm going to do is tangent 15 degrees, and then B, we'll do one with the sine or cosine one. So I'm going to pick sine, and we're going to do sine of let's do 112.5 degrees. Just a reminder, if you have the angle in radians and that is confusing to you, you can always just change it to degrees. So we can do one of these in radians. I'm just picking them in degrees. But if you see one in radians and it confuses you, you can always change it to degrees. I'll do one after I do these though. So starting off with tangent 15 degrees. If I want to use the half angle identity, I can pick any one of these for tangent alpha over 2. I'll tell you that this one is very easy to simplify for this type of problem. So that's the one that I'm going to work with today. So what I'm going to do is I'm going to use this identity, and I'm just going to write it out for us. 1 minus cosine alpha divided by sine alpha. And so I'm trying to find tangent 15 degrees, and that 15 degrees is supposed to equal the alpha over 2. So what we want to find is what's the angle that I would divide by 2 so that it equals 15. I'm going to say that again. What's the angle we divide by 2 so that it equals 15? Our angle here is going to be 30 degrees. So tangent 15 degrees is the same as saying tangent 30 degrees divided by 2. What this means for us is that this 30 degrees is my alpha in my identity. So when I go to the other side of the identity, I'll just plug 30 degrees in as alpha. And we know cosine and sine of 30 degrees. So that's the whole point, is that instead of using, 15 degrees, we're using a 30, 45, 60, or maybe something that at least has a reference of 30, 45, or 60. So I'm going to use the other side of the identity now. So I have 1 minus cosine 30 degrees divided by sine 30 degrees. I'm going to keep simplifying now. So I get 1 minus cosine of 30 is square root 3 over 2. Sine of 30 is 1 over 2. To simplify this, I'm going to, instead of dividing by 1/2, I'm going to multiply by 2, which is multiplying by the reciprocal or keep, change, flip. So I have 1 minus square root 3 over 2. And instead of dividing both of those by 1/2, I'm going to multiply both of them by 2. Distribute will give me 2 minus 2 root 3 over 2. So I get 2 minus square root 3. This is much easier to simplify than what we did in the last section. And just to check this in my calculator, if I type this in the calculator, I get 0.27. If I type in tangent 15, I get 0.27. So I'm just using that decimal to check it in my calculator. I'm not making that my answer because that's not an exact value. My exact value is that 2 minus square root. Now you could have also used the sum or difference identity for tangent here. I like the half angle identity for tangent when doing exact value problems like this, just because it's way easier to simplify than what we did in the last video. Next one, we're going to do sine of 112.5 degrees. When you see this 0.5, this means that you probably need to use the half angle identity. You really can't use a sum and difference here because when you use the sum and difference, you want both the angles you pick to be references of 30, 45, and 60. None of those and none of the angles that have those as references are going to be able to give you that 0.5. So this is a case where we have sine, and it would be the same story if it was cosine, where you have to use one of the half angle identities. Like you can't use a sum and difference for this one. So again, I'm going to apply this half angle identity. So I'm going to write my identity right here just so we can see it. I have plus or minus square root 1 minus cosine alpha over 2. This plus or minus right here on the outside of that square root is determined by what quadrant this angle is in. So 112.5 is going to be in quadrant 2. It's bigger than 90 but less than 180. Sine is positive in quadrant 2, so that's going to make this positive. Let's say if that had been in quadrant 3 or quadrant 4, then we would have picked the negative on the outside of that square root because sine would be negative in those quadrants. Now I need to figure out what my alpha needs to be. So if I'm saying this, I need something that I would divide by 2 to get 112.5. What you can do if you ever struggle with finding what this is, like it was kind of easy to just think about it for the 30, but you can always take the 112.5 and set it equal to alpha over 2, and then solve for alpha by multiplying both sides by 2. This gives me 225 equals alpha. And 225 has a reference of 45. So that's why we want to use this identity, because we're able to, instead of dealing with 112.5, we're dealing with 225, which has the reference. So now I'm going to plug in my identity. So I have sine 112.5 degrees is equal to sine 225 over 2. It's the left side of my identity. Now I'm going to plug in my alpha into the right side. And we have that positive that we chose because it was in quadrant 2. I have square root 1 minus cosine 225 divided by 2. Cosine 225, we do have to be careful here. 225 is in quadrant 3. Has a reference of 45. Since it's in quadrant 3, cosine is going to have to be negative there. So this will be negative square root 2 over 2 divided by 2. And now we're simplifying. So I have equals the square root 1 plus root 2 over 2 divided by 2. Instead of dividing by 2, I'm going to multiply by 1/2. This is all in the square root still. This is going to give me 1/2 plus square root 2 over 4. Come up here for space. To combine fractions, I need common denominators. I can make 1/2 2 over 4 plus root 2 over 4. This will give me 2 plus root 2 over 4. I can do the square root of 4, and I can break that square root to the numerator and denominator. So I get square root 2 plus square root 2 over 2. I took the square root of 4, that's why I got that 2 at the bottom, and now the square root isn't touching the denominator. And this is the simplest we can get with this. And just to type this in my calculator, I get 0.92. And if I type in sine of 112.5, I also get 0.92. So that means that my answer is correct. I always do recommend trying to just type it in and make sure that your work is correct there. If you're getting different values, then you've definitely made a mistake somewhere. Just one more of these. I can do a cosine one, and we'll do pi over 8. Just do a radians one. I recommend that you pause the video and try to do this one on your own, but of course I will go ahead and do it. So I'm trying to apply my identity. So my identity is cosine alpha over 2 equals plus or minus square root 1 plus cosine alpha over 2. I need my alpha over 2 to equal the pi over 8. So I'm looking for my alpha would be whatever I divide by 2 that equals pi over 8. So I can do pi over 8 equals alpha over 2. Multiply by that 2. This gives me pi over 4 equals my alpha. So cosine pi over 8 is equal to cosine pi over 4 divided by 2. So on the other side of my identity, I'll have 1 plus cosine pi over 4 divided by 2. Pi over 8 is in quadrant 1, so this is still going to be positive on the outside. The rest of this is simplifying, so I get square root 1 plus cosine pi over 4 is root 2 over 2 divided by 2. I'm going to change that again to multiplying by 1/2. Get 1/2 plus root 2 over 4 square root 2 over 4 plus square root 2 over 4 square root 2 plus square root 2 over 4. So this equals square root 2 plus square root 2 divided by 2. Kind of funny that they ended up as the same answer. Because they both technically have the same reference. I'm just checking my work here, making sure everything looks good. I type in pi divided by 8, and then do cosine of that. 0.99. Oh, I see, I see. Be careful. This is still... just now when I was trying to check myself in my calculator, I'm using my phone calculator to type this in. I was still in degrees when I was typing in cosine pi over 8, so I was getting 0.99, and that's not the answer that I got, so I was thinking there was something wrong. but I needed to switch my calculator into radians. So be careful whenever you're checking yourself. If you type something in and it has pi in it, you need to make sure you're in radians. If you type something in with degrees, make sure you're in degrees. There is one more thing I wanted to say about this one. Oh, just like I said earlier, if the radians are hard to work with for you, you can always switch that to degrees. So pi over 8, if I wanted to switch it to degrees, I'd multiply by 180 over pi. So this would give me 22.5 degrees. And all the work would be exactly the same. The only thing that would change is instead of writing pi over 4, we would have been writing 45 degrees. But those are the same thing, just different degrees versus radians. This is it for the exact value type problems in this section. So now we're going to do a different type of identities problem, but still with the half angle identities. So this is example 2. This one says if sine alpha is equal to negative 4 over 7 and alpha is between pi and 3 pi over 2, we want to find sine alpha over 2, cosine alpha over 2, and tangent alpha over 2. So this is the example. I talked about this in the last section, that sometimes when we use identities, we don't actually know our angle, and we aren't going to find our angle either. We're going to use the relationship of sine alpha to plug into some identities and potentially even make a triangle if we need to. So since I'm looking for sine alpha over 2, cosine alpha over 2, tangent alpha over 2, that should tell you that you need those identities. So sine alpha over 2, I'm going to write my identity. It's plus or minus the square root. 1 minus cosine alpha over 2. My cosine alpha over 2 is plus or minus square root 1 plus cosine alpha over 2. And for the tangent half angle identity, you have two options. You can use one of the identities we wrote earlier, or I will also tell you that tangent's the same as sine over cosine. So I'm already going to have to find sine alpha over 2 and cosine alpha over 2. So you could plug those in to here. If those look hard to simplify though, we can also use one of the identities from earlier. So I'll say we could use the 1 minus cosine alpha over sine alpha. That one's usually pretty easy to simplify, so I like using that one a lot. So for tangent, we have really a lot of options, but some might be easier to simplify than others. So I'm going to start with the sine alpha over 2. As I look at this one, to be able to use this identity, I really need cosine of alpha. I don't currently have cosine of alpha, but I do have sine of alpha. Since I have sine of alpha, I can use this relationship to make a triangle. This will also tell me what quadrant my alpha is supposed to be in. So I'm going to make my triangle up here. So between pi and 3 pi over 2 is where my alpha is, so somewhere in here. So I'm going to make my triangle. Sine is opposite over hypotenuse, so my opposite side is going to be negative 4. My hypotenuse is 7. If I'm looking for cosine of alpha, then I need the adjacent side, which I don't currently have, but we can get the adjacent side by using Pythagorean theorem. So I have negative 4 squared plus x squared equals 7 squared. 16 plus x squared equals 49. X squared equals 33. So x equals square root 33, which cannot reduce, so we'll just leave it as is. So for my cosine alpha, I get square root 33 over 7. Also, watch out for any positives or negatives. This should be a negative since it's in the third quadrant. So cosine is going to be negative here. So then I can plug that into my identity. So I get plus or minus square root 1 minus negative square root 33 over 7 divided by 2. I'll deal with that plus or minus on the outside at the end of this. Get 1 plus square root 33 over 7. Instead of dividing by 2, I'm going to multiply by a half. Plus or minus square root 1/2 plus square root 33 over 14. One over 2, I can make this 7 over 14 plus square root 33 over 14. I get plus or minus square root 7 plus square root 33 over 14. Plus or minus. So it can't reduce at all. We would just have to leave it like this. Pretty messy. But if I come look up here, I do need to figure out whether it should be plus or minus at the end. To do that, I'm going to look at this right here. If alpha is supposed to be between pi and 3 pi over 2, if I divide everything in there by 2, I will get alpha over 2 less than, pi over 2 less than alpha over 2 less than 3 pi over 4. Pi over 2 is 90 degrees. 3 pi over 4 is right in the middle of quadrant 2. So that puts alpha over 2 somewhere in here. What this tells us is that we're in quadrant 2. Sine is positive in quadrant 2. So my final answer here is positive square root 7 plus square root 33 over 14. Technically, you could keep simplifying just a little bit here because you could rationalize that denominator. That's not really something that I worry too much about, though. Next, let's look at cosine alpha over 2. I already have cosine alpha, so I can just plug it right into my identity. I can also choose my plus or minus. Since we're in quadrant 2, cosine is negative in quadrant 2, so we're going to have the negative. So it'll be negative square root 1 plus square root 33 over 7 over 2. Don't forget your negative right there for that negative square root 33 over 7. So I get negative square root 1 minus square root 33 over 7 divided by 2. Simplifying this will be the same steps as with sine. The only difference is now we have a minus inside. So this is going to be square root 7 minus square root 33 over 14. I'm going to box in these answers. For my tangent, you have options here. You can use what you already have for sine alpha over 2 and cosine alpha over 2. I think that'll be hard to simplify. I'm just going to use the other identity. So 1 minus cosine alpha was negative square root 33 over 7 divided by sine of alpha, which they gave us, was negative 4 over 7. I get 7 over 7 plus square root 33 over 7 divided by negative 4 over 7. Keep change flip. I get 7 over 7 plus square root 33 over 7 times negative 7 over 4. These 7's will cancel. Just to make that a little bit clearer, let me show a little bit more work there. Sometimes I get a little quick to cancel stuff out, but I really should show some more work. This is 7 plus square root 33 over 7 times negative 7 over 4. So now they can cancel. I'm left with negative 7 minus square root 33 over 4. This one was hard to simplify. Just a little messy looking, really. We're going to do another one kind of like this, but with the double angle identities, which I haven't given you yet, but I'll give you those in just a minute. So this is it for the half angles. So what you're going to see with half angles is sometimes maybe you're using the half angle identities to give the exact value of angle, or sometimes you're looking to actually use the identity, like you're looking for alpha over 2, cosine alpha over 2, or tangent alpha over 2. So you may need to use a triangle and be able to plug into the identity. Next, we're going to look at our double angle identities. And just a reminder, these are also on your identity sheet. So you do not need to memorize them, but I'm going to give them to you first. Your double angle identities say that sine 2 theta is equal to 2 sine theta cosine theta. Cosine 2 theta actually has a few options. You've got cosine squared theta minus sine squared theta, 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. So this one's kind of like with that tangent half angle where you had multiple options. This one has the same thing happen. And whatever one you're going to pick just depends on what you're using it for. Then I have my 2 theta in tangent. It's 2 tangent theta divided by 1 minus tangent squared theta. Double angle identities are not usually used for finding exact values of weird angles. These are more commonly used for questions like what we just did a second ago, or maybe in like verifying. They're used a lot in simplifying. So in our next section that we'll do, which is solving equations, we can use these in that sometimes to simplify. So they just have different uses. It really just depends on the question. But I'll go ahead and do our problem first. So this one is example 3. I just needed to check. Example 3. So this one says, given that sine theta is equal to 2 over 3 and theta is in quadrant 2, find exact value of sine 2 theta, cosine 2 theta, tangent 2 theta. Very similar to our last problem, but now we have the double angle identities to use. I'm going to write my identities up at the top. So I have sine 2 theta is equal to 2 sine theta cosine theta. And let's just start with that one first, and then I'll write the others after. If I look at my identity here, I have sine theta already. They gave me that. I don't have cosine theta though, but I can go get it using the relationship that I can make out of the triangle. So they tell me that theta is in quadrant 2. So I'm going to draw my coordinate plane. Theta is in quadrant 2, so I put it about here. Let's make my triangle. They gave me sine, which is opposite over hypotenuse. So my opposite side is 2. My hypotenuse is 3. I can go find that adjacent side by using Pythagorean theorem. Get x squared equals 5. So x equals square root of 5. So my cosine of theta is negative square root 5 over 3. Negative because in quadrant 2 we have the negative x-axis. I'm going to go plug this all into my identity now. Sine theta is 2 over 3. Cosine theta, negative square root 5 over 3. I get negative 4 square root 5 over 9 for sine 2 theta. Next, we can go do cosine 2 theta. Now, like I said earlier, cosine 2 theta has a few different options. So you have some choices on which identity you want to use. It really doesn't matter which one. I guess it would be nice to use this 1 minus 2 sine squared theta, just because it's always nice to use given information over found information, but you'll get the same result. I'm just going to use the top one because why not? Maybe if you want to pause the video and try a different one and just see if you get the same answer as me. For cosine squared theta, so I plug in my cosine theta, so negative square root 5 over 3, and then I square it, minus sine theta, which was 2 over 3, and then squared. I get 5 over 9 minus 4 over 9. This gives me 1 over 9. Lastly, for my tangent 2 theta, you can use the identity, or for this one, because they aren't super terribly hard to simplify, I can just say that tangent 2 theta is sine 2 theta over cosine 2 theta. The sine 2 theta was negative 4 square root 5 over 9. Cosine 2 theta is 1 over 9. Multiply by the reciprocal here. So keep, change, flip. And I get my answer is negative 4 square root 5. Those 9s cancel out. This one's a bit easier to do. It's just that it had nicer numbers, and the identities are a lot easier to work with. It's just that they don't have all the square roots and everything. We had a little bit of square roots because of cosine theta, but the identities themselves didn't have a square root in there. You also didn't have the plus or minuses on the outside, so you didn't have to really figure out the quadrant part of it. You could just let the work do it for you. The only part we had to be careful about picking positive or negative is when we found that cosine theta. So this is just one example of using the double angle identities. You can also use the double angle identities to make more identities. Now this can be a little tricky. So let me write this out for you. Using the double angle to make more identities. So for instance, if we wanted to find sine 4 theta, this would be 2 sine 2 theta cosine 2 theta. So we're using the original sine 2 theta is 2 sine theta cosine theta. And if we want to double it, we can do 4 theta. What's really happening here is that we're saying this is the same as saying sine 2 times 2 theta. So we have 2 sine, and then instead of, since here it was theta and theta, here it would be 2 theta and 2 theta. I do think it's pretty tricky to make the new identities. It's not something I personally ask my trig students to do often, but if you are someone who's going into the calculus series, it does come up there. Another example is we could take sine theta, and this would be 2 sine theta over 2 times cosine theta over 2. If we did one with cosine, cosine 6 theta is equal to, I'll write out the original for us over here. So cosine 2 theta is equal to cosine squared theta minus sine squared theta. So if I change this to cosine 3 times 2 theta, or it might be better to see it as 2 times 3 theta. This 2 and this 2 are the same, but now everywhere I see a theta, I'm going to replace it with 3 theta. So I would get cosine squared 3 theta minus sine squared 3 theta. Again, this isn't really something I will ask my students to do, but it's possible. Another use for the double angle identities is we can use them when verifying. So let's do a verifying identity problem. This is example 4. We're going to verify the identity. Sine 3x is equal to 3 sine x minus 4 sine cubed x. This one is an interesting verifying because usually I tell y'all that you start with the side that has more stuff on it. In this case, we're actually going to start with the sine 3x side. So it looks smaller, but because now we know sum and difference identities, we know double angle identities, we'll be able to use that side and get to the other side a little bit easier. So we're going to start with our left-hand side. I'm going to start with sine 3x. And the first thing that we'll need to do here is we're going to try to use the addition identity. So I'm going to first make this into sine 2x plus x. So sine 3x is the same as sine 2x plus x. And then I'll use the sum and difference identity. So I'm going to put on the side here that I'm using the sum and difference identity. And we talked about that one in 6.2. So I get sine 2x cosine x plus cosine 2x sine x. And so what this did is it helped me create these two terms that I'm looking for. Now they're not quite, but just the fact that I have two terms gets me a little closer. Now if I look at where I'm trying to get to, I see that I only have x. I don't have any like two x's. So I'm going to replace my sine 2x and my cosine 2x with the double angle identities. So I'm replacing sine 2x. I'll put a note here. We're using the double angle here. So I have sine 2x is equal to 2 sine x cosine x. I'm also going to replace cosine 2x, which is cosine squared x minus sine squared x. I'm replacing those identities. So I have 2 sine x cosine x times cosine x plus cosine squared x minus sine squared x times sine x. A lot of this becomes algebra, and we will use a little bit more of identities, but this would be a good place to pause and just kind of try to work it out yourself. Here I get 2 sine x cosine squared x plus sine x cosine squared x minus sine cubed x. I can combine like terms here. So I'm going to do some algebra. And I get 3 sine x cosine squared x minus sine cubed x. These are good signs. This sine cubed matches this sine cubed. 3 sine matches 3 sine. The issue here is I somehow need to make 4 in front of that sine cubed, and I don't want to have cosine squared. So I can replace this cosine squared using the Pythagorean identity. So we have the identity that sine squared plus cosine squared equals 1. If I move over my sine squared, I get cosine squared x is equal to 1 minus sine squared x. I'm going to use this identity to replace this cosine squared, which again, the reason I'm doing that is because if I look at my goal, like I'm trying to get to my right-hand side, I don't have a cosine squared, so I'm trying to replace it with something. I have a bunch of sines, so I'm replacing it with sine. Get 1 minus sine squared x. And then I still have that minus sine cubed x. Now I can distribute this 3 sine x. So that'll give me 3 sine x minus 3 sine cubed x minus sine cubed x. These are like terms, so I can do some algebra and combine those like terms, which will give me 3 sine x minus 4 sine cubed x. This is equal to my right-hand side, so we are done. I'm going to zoom out a little bit so you can see the whole thing. This is a pretty hard verifying in my opinion. You know, it needs you to do a lot of identity replacements. You got to be pretty creative with this one. That's it for now for my double angle identities. We will see double angle identities again when we are solving equations. We'll do some where we use the double angle identities to simplify. But at least in this section, we're done with those for now. The last kind of identities we're going to talk about are our power reducing. It's exactly what it sounds like. These are used to reduce the powers. These come from the double angle identity, so I'm going to show you just one of them. So if I start off with cosine 2 theta is equal to 1 minus 2 sine squared theta. If I solve this for sine squared theta, I get 1 minus cosine 2 theta divided by 2 equal to sine squared theta. So these power reducing actually come from the double angle, but I'll just write all of them out for you. So sine 2 theta is equal to 1 minus cosine 2 theta divided by 2. Cosine squared theta is equal to 1 plus cosine 2 theta divided by 2. And of course we'll do a tangent. Tangent squared theta is equal to 1 minus cosine 2 theta divided by 1 plus cosine 2 theta. So these identities get rid of a power on your sine, cosine, or tangent. For those of you who may go into the calculus series, these are very common to see starting in Calculus 2, which is our 242 at Louisiana Tech. So these come up quite often in those classes. Yeah. We'll do one example of using these. These are kind of their own kind of example. In this class, we really don't use them for anything. I guess in a way, I'll kind of say we don't really use them for anything super practical. For instance, we're not using them to find the exact values of angles or anything like that. They're kind of just their own problem. So this one says write sine to the 4th x plus cosine squared x in terms of first powers of cosine. So your goal here is to get rid of the powers on the sine and cosine. And so at the end of this, you won't have any exponents and you'll just have cosines. So that's your goal at the end, is no exponents, only cosine. So I'm going to start off with, I have sine to the fourth x plus cosine squared x. First, I'm going to change this sine to the fourth x to sine squared x squared. And then I have that plus cosine squared x. The reason I changed this is because I have the identity for sine squared, not necessarily sine to the fourth. So now I can replace using those power reducing. So I'm going to use my power reducing identities here. Sine squared x is equal to 1 minus cosine 2x divided by 2, and that is still squared. My cosine squared becomes 1 plus cosine 2x divided by 2. Remember, when you square something, you're really multiplying it by itself. So this is 1 minus cosine 2x over 2 times 1 minus cosine 2x over 2. And then I just still have this 1 plus cosine 2x divided by 2. I'm doing some algebra here. If I want to expand these, so I'm going to have to FOIL the top, so I'm going to have to do some foiling here. The bottom will just multiply 2 times 2. So I get 1 minus cosine 2x minus cosine 2x plus cosine squared 2x, all divided by 4, plus 1 plus cosine 2x over 2. I'm going to do some more algebra just to simplify a little bit. I get 1 minus 2 cosine 2x plus cosine squared 2x, and that's all over 4. Plus, now I would like to make this second fraction here also have a denominator 4. That way I can put it all together. So I'm going to multiply this by 2 over 2. So that's going to give me 2 plus 2 cosine 2x over 4. That way I can put them together. I'm still just doing algebra. To put this all together, I get 1 minus 2 cosine 2x plus cosine squared 2x plus 2 plus 2 cosine 2x, all divided by 4. Negative 2 cosine 2x. and positive 2 cosine 2x will cancel out, and that leaves me with 1 plus 2, so 3, plus cosine squared 2x divided by 4. I'm going to have to deal with some more fractions for a moment, so I'm actually going to do something a little creative here. I'm going to pull this 4 denominator out to the front by saying that that's 1/4 times 3 plus cosine squared 2x. The reason I'm doing this is because I'm about to replace cosine 2x with another of the power reducing identity. So to do that, I'm going to end up with more fractions, and I don't really want a complex fraction. So cosine squared x is equal to 1 plus cosine x over, 2x over 2. If I make this cosine squared 2x, this would become 1 plus cosine 4x divided by 2. So I'm having to change the identity a little bit to fit my needs. So I get 1/4 times 3 plus 1 plus cosine 4x divided by 2. I'm going to multiply my 4th back in, so I get 3 over 4 plus 1 plus cosine 4x over 8, because that 4 times 2 gives me an 8 in that denominator. I need common denominators again, so I'm going to make this times 2 over 2, and then I'll be able to put it all together. So this is going to be 6 over 8 plus 1 plus cosine 4x over 8. I get 6 plus 1 plus cosine 4x all over 8, which equals 7 plus cosine 4x all divided by 8. A lot of this was just algebra. All of this algebra. I'm going to change my screen for a second so that you can see the whole thing a little bit easier. I'm going to zoom out some. This is a long problem. Lots of algebra. So again, the whole goal of this was to get rid of all the exponents. So anytime we had an exponent, we had to use the power reducing identity. And that also in turn gets rid of any signs and changes everything to cosine. And a lot of it was just simplifying. But that is it for this video. So I will see y'all in the next one, and I hope you have a great day.